lesson, we're going to look at mixtures of gases and how we use the properties of gases with chemical reactions and do simple stoichiometry problems with them. First off, I have an apparatus here, or a picture of an apparatus that shows a very simple setup that we use for collecting gas just by water displacement. So here's some solid potassium chlorate. They're heating it up with a burner. And chlorates decompose to give off oxygen gas. And one way you could imagine doing this is filling a container with water, and then by water displacement, you can collect the gas. However, anytime you do this, you will always have some amount of water vapor present because there was water there in the beginning. Some of it evaporates into that container. So this is where we first have to deal with a mixture of gases. And to handle this, we can use what's called Dalton's law of partial pressures. Pressures are additive. The total pressure of a system is just the sum of the partial pressures of the individual components of whatever makes up that mixture. This is not true for every property, but just like mass, pressures are additive as well. So I could actually modify this and look at the ideal gas law, rearrange and solve for P. You get nRT over V. What is the partial pressure of a substance? Well, it's just based on the moles of that substance. Pressure is directly proportional to moles, which means that mole to mole ratios become pressure to pressure ratios. And we'll see that this is very useful when we look at chemical reactions involving multiple gaseous species. So let's actually dive into this setup a little bit more and give ourselves some data to look at. Let's say we decompose a sample of potassium chlorate. We make potassium chloride an oxygen gas. That's what we care about, the oxygen. I collect a volume of it at some temperature and some pressure, and I know how much of that is due to the water vapor. First of all, what's the reaction that occurs? Well, potassium chlorate is KClO3. They tell us that it decomposes to make potassium chloride and oxygen gas. And then if you go back and balance that, you need 2 potassium chlorates to make 2 potassium chlorides and 3 oxygens. Then it says, what's the partial pressure of just the oxygen? Well, 21 torr of that collection of gas is the water, and the total is 754. So the pressure of just the oxygen is going to be the total pressure minus the pressure that's due to just the water vapor. So I get 754 minus 21, which is 733 millimeters of mercury. They want it in atmospheres. So remember from our previous lesson, take a millimeter of mercury and then just divide by 760. You'll get it into atmospheres. I'm just going to write the numerical answer. You get 0.964 ATMs after you convert it into atmospheres. So now can we use this to do something stoichiometric? How much potassium chlorate was used in this reaction? We'll look at how much oxygen we got out of it. We know the pressure of the oxygen. We also know the volume of the oxygen, and we know the temperature of the oxygen. So we can get the moles of the oxygen. So the moles of the O2, that's the pressure times the volume, divided by R times T. The pressure we just got, 0.964 atmospheres. The volume, 0.650 liters. The R value from our previous unit is our previous lesson, 0.08206. And the temperature, don't forget to convert this 22 into Kelvin. That becomes 295. And when you do that, you get 0.0259. That's moles, specifically moles of O2. How do I take my moles of oxygen and turn it into a mass of potassium chlorate? Well, let's first figure out how many moles of potassium chlorate I have. There's a 2 to 3 ratio. So I can just take this numerical value and say there's 2 moles of KClO3 divided by 3 moles of O2, and then to turn it into a mass, get the molar mass of potassium chlorate. 1 potassium plus 1 chlorine and 3 oxygens is 122.55 grams per mole. You plug all that in, you get 2.12 grams of the chlorate. So all we did was figure out the mass of a substance that would let us turn it into a pressure of a gas. Remember, a pressure is just another way of saying an amount of a gas. You really get to think of them the same way you think about moles and grams of a substance. 0.964 atmospheres of O2, that's just another way of saying that much O2 is present. And we had to correct for the water vapor pressure because we were collecting it above water. Okay, so jot all that down and then hit pause and see if you could do the next question, which is very similar. They're collecting oxygen again by water displacement, and they want the reaction that occurs and something stoichiometric about the beginning. Hit pause and try that now. Okay, let's see how you did. So we have a solution of hydrogen peroxide. We mix it with sodium hypochlorite to make water, chloride, and oxygen. What's the reaction that occurs? Hydrogen peroxide, remember, is H2O2. Sodium hypochlorite is NaOCl, but sodium is going to be a spectator, so I'm just going to write hypochlorite ion, OCl minus. They tell me this turns into water, chloride, and oxygen gas. This is actually a redox reaction, isn't it? The oxygen changes and the chloride changes, but it's already balanced. You got lucky. 1 to 1 becomes 1 to 1 to 1. Next, they say, what amount of the peroxide do we need to make 40 milliliters of the oxygen gas? And this time, we're not going to do that water vapor correction. We should, but they didn't give us that information, so let's just assume that all of it is O2. Given excess hypochlorite and 0.8 molar peroxide, how much do we need? Well, look at what they give us. They give us the volume of the gas, they give us the pressure of the gas, and they give us the temperature of the gas. So just like last time, we can solve for the moles. So the moles of the O2 is pressure volume over R times T. Our pressure is 0.988 atm. Our volume, 40 milliliters. Don't forget to turn that into liters. So you get 0.0400 liters divided by the R value. That's 0.08206 liters atms per mole Kelvin. And then the temperature is already given in Kelvin. That's 298. And when you type all that out, you get 0.00162 moles of O2, but they want a volume of the other reactant of the peroxide, which if I look at the figure, it's a molarity of peroxide given from our previous unit. Remember, molarity is moles per liter. So first I need to turn this moles of O2 into moles of peroxide, and then we'll turn that into a volume using the molarity. The mole to mole ratio is 1, but I'll write it out anyway. There's 1 mole of peroxide for every 1 mole of oxygen. And then the molarity, if I want to get out of moles of peroxide and into a volume, I could use the molarity, 0.8, although I can tell from these numbers I'm going to get a really small number of liters. So I'm going to change that liter in the numerator to 1,000 milliliters. That'll just give me a nicer number to look at in the end, and you get 2.02 milliliters of the peroxide solution. So this is just like the previous question where we took a volume, pressure, and temperature of a gas, we turned it into the moles of that substance, used the mole to mole ratio to get how much of a reactant, and then just a throwback to our previous unit on how to incorporate molarity to turn it into a volume of that peroxide solution. So that's how we use gases in chemical reactions. Now, what about mixing multiple gases? We already talked about Dalton's law of partial pressure. Let's say I have a sample of oxygen contained in some fixed 5 liters at a temperature and 0.8 atmospheres, and some other container of nitrogen, it's 5 liters and 1 atm. Then I mix them and I put them in the same container with the same volume, 5 liters. It wants the new pressure of each gas after you mix them together. There's no reaction happening here, so I get to use the combined gas law because there's no chemical change like the problems up above. Remember, the combined gas law is simply P1 V1 over T1 is equal to P2 V2 over T2. And I'm going to use that for each gas, but look again at what's changing. The volume of each gas is actually kept the same. So I can actually cross out V1 and V2. It doesn't change. They cancel out of that equation. What about the temperature? Well, if the temperature is the same, it's at constant temperature, then I have no change in temperature either. So there's actually no change in the pressure. The pressure of the gas going in is going to be the same for each gas coming out. So the new pressure of the oxygen, P of O2, is the same as what it was in the beginning. It looks like 0.8. So it's 0.8 ATMs. And then likewise for the nitrogen, it's going to be the same as it was before. The pressure of the nitrogen was 1 atmosphere. It's still 1 atmosphere. If your volume is the same and then the pressure, the temperature is the same, then the pressure won't change. Even though there's an extra gas in there, yes, it doesn't matter if multiple gases are present. Remember, gases are selfish. So they fill up the entire container, the entire volume of whatever container that they're in, and they exert some pressure that we call a partial pressure due to that gas. If you throw in another type of gas, here's just 2 different types of gas species, they don't affect each other's partial pressures. Those are only based on how much of that particular gas is present, what temperature it's at, and what volume it's at. And those things didn't change. So the initial pressure is the final pressure for the individual gases. But what's the total pressure in the end? Well, the total pressure is just the sum of the two. So the total would be the O2 plus the N2. So 0.8 plus 1 is simply 1.8 ATM. Okay, there's one more left to do on this lesson. This one actually does involve a chemical reaction, and I'd like you to hit pause once more and see if you can figure out how to do this last question that involves making nitrogen dioxide from nitric oxide and oxygen. Hit pause and try that now. Okay, let's check and see how you did. So this gives us a chemical reaction. It combines pressures of different species, and it first wants the reaction, which is between O2 and NO to make NO2. Don't forget to balance. You'll need 2 nitric oxides, and you'll make 2 nitrogen dioxides. So that's all we're looking for part A, the net reaction. And here it is represented in a particle diagram. Now, what's the final pressure after a reaction occurs? Well, notice they don't give me the volume and temperature, but they do say it's constant. So remember earlier we said that mole-to-mole ratios get to be pressure-to-pressure ratios. We can just use those pressures as if they were moles, as if they were amounts of substance. We have 4 atmospheres of oxygen reacting with 8 atmospheres of nitric oxide, which is exactly a 1-to-2 ratio, and that's exactly what we need. So you're going to lose all the oxygen, you're going to lose all the nitric oxide, and you're going to gain a stoichiometric amount of the nitrogen dioxide. You're going to have 8 atmospheres of the NO2 in the end. We don't need to use the ideal gas law to convert into moles and then convert back out of it into pressure because we're at a constant volume and temperature. So pressure ratios get to turn into mole-to-mole ratios. P to P ratios can be used in place of mole-to-mole ratios. That's because they're gases and because the volume and temperature are constant. If the volume and temperature change, we'd have to use the ideal gas law to get into something like moles and then back out into one of the other properties. Okay, so that's how we handle multiple gases when there's a reaction, when there's no reaction, and how we combine it with stoichiometry problems for generating gases by water displacement and correcting for things like water vapor pressure using Dalton's law of partial pressures. Thanks for watching.